Hi everyone, welcome to Mostly Math. Today we will be deriving the equations of motion for the action I've written above here in two ways. We're going to use the Euler-Lagrange equations and we're also going to vary it from scratch. Okay, let's talk about x plus and x minus. What are these things? Well, for the purposes of this video, it doesn't really matter. But if you need to know, these are useful in special relativity. They'll be useful. X plus and minus are defined to be the following. I guess it doesn't really matter where you put the pluses and minus signs. It's up to you. X plus or minus to be t plus or minus x. And because we have a t and an x together, this is going to be useful for special relativity, and you can also find actions like this to be useful in string theory as well. This is probably one of the most simple actions available. In particular, this one is proportional to a more familiar action. This one, if we have d phi by dt squared minus d phi by dx squared. It's going to give you the same equations of motion. It's going to be proportional to this one. But as you can see, this one is first order in the derivative, so it's even easier to do. Okay, there's some background on why we would consider such an action. Now let's go ahead and begin our first method of showing it, or finding the equations of motion. Let's check out the Euler-Lagrange equations. For these, we have d mu by dl by d phi by, abbreviating this, d mu phi minus dl by d phi is equal to 0 for some field phi. This is true for actions of the following form. If we have some d-dimensional integral of a Lagrangian with one particular functional phi, and then we have all the derivatives, where there could be d mu's, for example. Yep, these are the Euler-Lagrange equations for actions of this type. You are most likely used to seeing these, which we're not going to use. Probably used to seeing this one. We have I'll write in the following form: dl by dq dot is equal to dl by dq if we had a single variable action where L is just a function of phi and then d phi by dx. And what I like about this formulation is it's easy to remember because you can think of the dots as canceling, which is really interesting. Obviously, if you wanted to, you could write this out as d by t dt dl by dq dot. They're the same thing. I like to remember it this way because the dots cancel. It's pretty funny. It's not true though. Okay, so now we're going to use these Lagrange equations, which let us handle more than one variable being integrated over here. And the equation for only two is going to be the following. We're going to have, for mu is equal to x plus and x minus, then we're going to have d by dx plus variational derivative L with respect to d phi by dx plus another term here, d by dx minus variational of L with respect to d phi by dx minus, and we have one final term, variational of L with respect to phi itself. Okay, let's start plugging in terms here. Obviously, this is just L here, the product of two derivatives, and there are no phi's in sight. There are phi's here, of course, but they're always being acted on by a derivative, so this term is 0. And Let's look at this term first. Well, if we take the x plus derivative, we have x minus. So this becomes a second order derivative. And we're setting these equal to 0, of course. Of course, we're going to be setting gamma equal to 0. So then we have 0 is equal to d squared phi by dx plus dx minus here. Since we just talked, it's going to be a second order derivative. Same situation here. If we do the x minus derivative, this goes away and we have a plus. So we have the same thing again, basically. Plus d squared phi by dx plus dx minus, which we can just write as 2 d squared phi by dx plus dx minus. And therefore we can conclude, upon canceling the 2's, that d squared phi by dx plus dx minus is equal to 0. This is the equation of motion that we saw. In this video, we aren't going to solve the equation of motion, but it's pretty easy to do. It's just a second order differential equation, homogeneous. And this is my favorite method to use when authors speak of varying the action. Sometimes they don't mean this though. Sometimes they want you to just vary the action from scratch and push the delta through, as it were. So we'll also do that method right now. Let's go ahead and do the same thing for that method. So, and what comes next, just recall that delta only acts on phi. It doesn't act on the x's. So we're going to do any derivatives that involve the x's by the chain rule, then eventually multiply by delta phi. We'll see that in varying it from scratch, we're not going to use the Euler-Lagrange equations because that's actually how you can derive those equations. And we're going to have to use some more mathematical techniques, which we'll get to. Okay, so if I just go ahead and set 0 be equal to delta s, well, this is the same thing as, since the deltas I said act only on phi, nothing else, we can just carry it through. Delta of this expression and now we can use the chain rule to simplify it further. So we're going to have the delta act on this phi first and then this one second to get two terms. It is now dx plus dx minus. We have d phi by dx plus d delta phi by dx minus. It's very important. So we have that partial and the delta commute because, like I said, delta acts only on phi. So it can just go straight through the derivatives. We don't care about that. Plus d delta phi by dx plus d phi by dx minus. Excellent. Okay, now some of you can see where this is going. We have two very similar terms here, both of them containing only first order derivatives on phi, just like the action. But we know that the equations of motion has to be second order. So in these situations, pretty much there's only one technique that you can do. You want to peel off the x derivative from the phi and put it on the other x derivative, because we just saw that's what the answer is. So we're actually going to integrate by parts twice. Once for this integral and once for this integral. I'm just going to write them out as a single step. And of course, when we integrate by parts, there is going to be an overall minus sign. Since we're physicists, we always assume the boundary terms are 0, since most of the time they are. There are certain situations in which they're not, but we don't care about this here. Basically, the boundary term, we are saying that d phi by dx plus d phi by dx minus. If we evaluate this at x plus or minus is equal to infinity, and then x plus or minus is equal to negative infinity, whatever the appropriate limits are, it's going to be 0. So we're just saying that we don't care about the boundary terms. Since if we're going to generalize this to quantum mechanics, we have to have the wave functions be normalizable, so they have to go to the limits at plus or minus infinity. I'm not sure if these x pluses and minuses really start at infinity. It could be 0 to infinity. I don't know. It doesn't matter. It really doesn't matter. Okay, let's continue. So we have the overall minus sign, and now we have what we know to be the answer: d squared phi by dx plus dx minus, and we have the same thing again, plus d squared phi by dx plus dx minus, and we see we get twice the same thing here, so just write it out. Minus 2 integral d, oh sorry, I forgot an important step. This needs to be multiplied by a delta phi. But that was the entire point of integrating by parts, to get the delta phi by itself. Plus dx minus d squared phi by dx plus dx minus delta phi. And now we're going to use the fundamental lemma of the calculus of variations, which states if we have something integrated over all space multiplied by an arbitrary variation of the function, the integrand is going to be 0. So we obtain the equations of motion from before. Second order derivative combination is equal to 0. So if you notice, this one took me a bit longer. It's up to you to decide which method you prefer. Many authors of textbooks seem to prefer this method. I'm not really sure why. I prefer to just write out the appropriate Euler-Lagrange equations and then plug in the variables. It's much more mechanical procedure. I guess some authors enjoy doing things from scratch, say how I could enjoy being able to compute the x squared derivative as being 2x from scratch, by example, like we covered on a previous video. But yeah, definitely tell me in the comments which one you like better, and hopefully this was a good example of how you can use the Euler-Lagrange equations for more than one variable being integrated over, and also how you can vary it from scratch. I really wish someone would have given me an example like this when I was first learning about these subjects. It really helps to see an actual person do it so that you can feel like you can do it too. And you can. And if you enjoyed this, feel free to subscribe. I'll see you next time.